This next chapter, we're going to look at what solutions are and what chemical processes come together to make these mixtures of solutions. A solution is defined as a homogeneous mixture. And remember, a homogeneous mixture means it looks the same. It looks like one component, yet it's made up of a mixture of two or more substances. Those two substances are a solute, and the solute is the substance that gets dissolved, and a solvent. The solvent is the substance that does the dissolving. So, for example, we're mixing sugar and water. The water is the solvent, and the sugar is the solute. Usually, if you have a liquid and a solid, the solid is going to be the solute, the liquid is going to be the solvent. If you're combining two liquids together to make a solution, the one in the greater amount is going to be the solvent, and the least amount is going to be the solute. But those are the two components of a solution. So a solution is homogeneous, like we said. They contain very small particles, and that's why we can't see those particles in a solution. That's why it looks like one substance. And solutions do not display what we call the Tyndall effect. Now, if we look up here in the upper right-hand corner, you see this substance where we're shining a light through the liquid, kind of like a headlight going through fog. This is the Tyndall effect, when you can see the beam of the light. This substance does not display the Tyndall effect. So if we were looking to see which of these two substances were solutions, we would say this beaker right here, or this jar, contains a solution because there is no Tyndall effect. This one is not a solution. It's going to be something called a colloid that we'll talk about in a couple minutes. But also in a solution, the particles do not settle out. And we have an example here of rubbing alcohol, which is a combination of isopropyl alcohol and water. Other solutions, if you think of a bottle of Gatorade, that's a solution, or a Pepsi. There are different types of solutions. We can have solutions made up of all gases. Think of the air that we breathe. It's a solution of nitrogen and oxygen and carbon dioxide, all mixed evenly, a homogeneous mixture. If you look at a carbonated beverage where we have a gas in a liquid solution, because we dissolve the carbon dioxide in the liquid to make it carbonated. And then we can have solutions of two liquids together, such as ammonia and water as a cleaning substance, or a liquid in a solid like a slushy, where you have the solid ice with a liquid that's homogeneously mixed. And then we can have even solid solutions, which we call alloys. And by an alloy, we mean two solids that have been melted, poured together, and allowed to solidify again, such as brass, which is a mixture of copper and zinc. And usually around our houses, we have a lot of brass fittings, whether they be doorknobs or faucet handles. But those are combinations of copper and zinc metal melted and mixed together. We also have bronze, which is a combination of copper and tin. So metal solutions are called alloys. Then we have a substance that's called a colloid. Now, a colloid looks like a solution, but it's heterogeneous, which means it's not evenly distributed. Contains medium-sized particles and does display the Tyndall effect. Now, an example of a colloid, and you see those examples here, milk is used as an example of a colloid. And you're saying, well, how does a milk look like a colloid? Well, think of milk that's expired. That maybe you have milk in your fridge, you go on vacation for a week or two, you come back, and that milk separates. All the solid particles come to the bottom, and it's left with liquid on top. We usually just say the milk's spoiled. But because it separates, we know that it's a colloid. Because milk contains proteins and fat globules along with the liquid. It's actually somewhat of a mixture. That's why when you look at a milk carton, it says it's homogenized. because it's a heterogeneous mixture, but in the milk processing plants, they homogenize it so it doesn't separate out. So milk is a colloid, jello is a colloid, and fog is a colloid. And if you think of driving through fog, you have to use your low beam headlights, and you can see those beams of headlights as they travel through the fog, displaying the Tyndall effect. So colloids are substances that look like solutions, but will eventually settle out. And then we have a suspension, which contains very large particles. And think, you see the picture here of the lemonade or orange juice with pulp in it, or a mud puddle. Something where you're going to see those large particles and they're going to settle out. That would be a suspension. So be able to distinguish between those three types, the solutions, the colloids, and suspensions, and be able to place substances into their proper categories. Now let's take a look at solubility. Solubility is the effect of a substance dissolving in another substance, how a solute dissolves into a solvent. And there are some factors that affect the rate of dissolving. One of those factors is the amount of surface area. So think if you're making a pitcher of Kool-Aid and you dump your sugar in there. If you got a big clump of sugar, you want to break it up. You want to crush it. And by doing that, what we're doing is we're increasing the surface area. We're allowing more area of contact between the water that's acting as the solvent and the sugar that's the solute. The more area of contact there is, the quicker that it's going to dissolve. So we want to increase that surface area. We also want to stir the solution or shake the solution. We want to agitate the solution. And again, that allows the water molecules to come into more contact with the solute molecules in order to dissolve it. So we can increase the surface area, we can agitate the solution, or we can heat it up. And by heating up the solution, we're causing those particles to move more quickly and likewise causing them to come into contact more often. So these three factors affect the rate of dissolving, how quickly something dissolves. Think of the phrase like dissolves like. And remember back, goodness, in the fall, we're talking about polar and nonpolar molecules. Polar substances dissolve other polar substances. Water is a polar molecule. Water can dissolve other polar molecules, such as salt, such as sugar, such as isopropyl alcohol. Oil is a nonpolar molecule. Oil cannot be dissolved in water because water is polar and oil is nonpolar. Oil and water do not mix. The reason is they're not alike. So when we say like dissolves like, we mean polar substances can dissolve other polar things, and nonpolar substances can dissolve nonpolar things. So if you get grease or dirt on your clothes or somewhere and you want to get them out, you have to use a nonpolar solvent, something like paint thinner or turpentine or maybe acetone or sometimes even gasoline, and those will dissolve the nonpolar substances. So like dissolves like. We also say liquids may be miscible or immiscible. Miscible means they mutually dissolve in one another. Immiscible means they don't dissolve in one another. Oil and water are immiscible. They do not dissolve in each other. Oil and alcohol are miscible. They do dissolve in each other. So those are two vocabulary words that you should commit to memory. We'll also put solutions into one of three different categories, either unsaturated, saturated, or supersaturated. An unsaturated solution can dissolve more substances. It can hold more. A saturated solution is basically holding as much solute as it can possibly hold. Think of a sponge. A sponge absorbs water. And there becomes a point when the sponge just can't hold any more water because we say it's saturated. Or in the springtime here, we can think of the ground when we get so much rain that the water starts to puddle up on the ground. That's when the ground has become saturated. It can't hold anymore. So if we're adding sugar to water, the first amount of sugar that we put in is going to dissolve, and we're not going to see it. That's when the solution is unsaturated. But there's going to come a point when the solution becomes saturated and it can't hold any more sugar. And then you're going to see the sugar just start to pile up down here on the bottom because the solution can't dissolve anymore. So we say it's saturated. Now a supersaturated solution means it's actually holding more solute than what it actually should at that temperature. And you're going to see crystallization form. So the concentration is low when it's unsaturated, increases when it's saturated, and is extremely high when it is supersaturated. So again, know these three terms as far as vocabulary goes and be able to classify different substances into those three. And in the next lecture video, we're going to look at solubility curves and how we can determine if something is unsaturated, saturated, or supersaturated. The solubility of a substance is measured in how many grams of a solute we can dissolve in 100 grams of solvent at a given temperature. And the temperature is going to dictate the amount of solubility. It varies with temperature, and it's based on a saturated solution. Okay, so if we look at this solubility curve here, the solubility graph, we have temperature on the x-axis and grams of solute per 100 grams of water on the y-axis. Each one of these lines will tell us how many grams of the substance we can dissolve in 100 milliliters of water at a given temperature. So if we take this curve for sodium nitrate, right here, if we have 100 milliliters of water at 30 degrees Celsius, we follow this up and we see that we can dissolve about 94 grams of sodium nitrate in 100 grams of water at 30 degrees Celsius. Now for potassium nitrate, if we look at this right here, we can only dissolve 47 or so grams of potassium nitrate in water, or in 100 milliliters of water. The solubilities of these two substances are different. Now anywhere below the lines, if we're adding in potassium nitrate as you did in the lab, anywhere from here up to here, we say the solution is unsaturated. It can hold more. But once we get to the line, now we have a saturated solution, and we can't hold anymore. To make a saturated solution, what we have to do is we heat the substance up. So let's say we heat the water up to 60 degrees, and we dissolve 110 grams of potassium nitrate. So we have a saturated solution. Then we allow the solution to cool. And if it cools down to 30 degrees, we still have 110 grams of potassium nitrate in the solution, but it's saturated at 47 grams. So that's when we say we have a supersaturated solution. Notice the solid lines represent solids, and they almost all increase their solubility with an increase in temperature. They go up, some more than others, but they all increase with temperature. Gases, however, decrease with increasing temperature. So the solubility of sulfur dioxide or ammonia actually decrease in water as we increase the temperature. So the solubility of solids increase with an increase in temperature. The solubility of gases and liquids decrease with an increase in temperature. Okay. You don't need to memorize a chart like this, but what we need to be able to do is interpret a solubility curve like this. So if you're given this graph, can you answer questions regarding specific compounds and how many grams of a substance you can dissolve in water at a given temperature? That's what we want to be able to do.